Now, they could save the time. All right, so we're going to. They have these huge TVs here, and you're going to be 1,000 of views. So I may shift a little bit over here. And there's Miss Hope. Hi, Jen. All right, so we'll wait for everyone. Oh, Jen, did you happen to see my text I just sent you about the date of the middle school visits? How about that? Now, can you hear me?
Can you hear us?
I can hear you. Can you hear me?
I don't hear you. Let me.
How about that? Yeah, nothing.
We've had trouble with our speakers.
So it may be you, as any other sites, can anyone else?
So I can hear you on my.
Our audio is going.
I can hear you on my desktop, but I can't hear you through my speakers.
Okay.
Can you talk some more? Let me see if I can get my.
I would love to talk. Hi, Dr. Peppers.
there.
I'd like
Hi.
the TIE fighter that's above your head. It's behind your head now. Does anyone know what TIE stands for? It's an acronym. TIE. Like only the largest nerds get this right. TIE.
I'm Star Trek, so.
Okay. Oh, are you watching?
No, yeah.
It's fun. It absolutely is fun. All right. Hi, Julia. All right. I believe everyone is in. I'm hopeful that your sound systems are working very fine. You can see right behind my shoulder, and I am in a hole, and he's at normal height. That's so yeah. If I stood up, then it would. No. So we have the pleasure today. We have a guest speaker today. Dr. Edward Murphy is here from University of Virginia. He is in the astronomy department. He is currently involved with research with NASA, which he will share with you very soon. His background is his undergraduate. He got from the University of Illinois Urbana-Champaign, and I believe it was 86. 89, he made his way here to Virginia. He got his master's as well as his doctorate right in the 90s there in astronomy. And so he has stayed here. He has outreach programs. This is part of his outreach. He is very interested in making connections with the general public as well as students. And if you are in any ways interested in thinking that astronomy is something that you want to explore in the future, please make connections. Please get his email. We will share that with you. It's a very easy email to remember. So we will share that with you guys towards the end, and we will have questions at the end. Today, the topic is going to somewhat tie into chemistry in that how did all of the elements get here on Earth? So the origins of elements, that's something that we take for granted, but how did they all perfectly align and get here? And so that is what Dr. Murphy is going to be presenting to us today. I give you Dr. Murphy. Thank you guys so much. Oh, there is a waiting room. All right. Oh, let's get Mr. Kelly over here real quick. Sorry. Thank you for letting me know. Then we'll go share the screen. You should then be able to get to the screen that you can. Okay. All right. Thank you, guys.
All right, thank you, Trent. I was gonna ask, is this, I think like the 10th year we've done this?
No, I believe so. My son is turning 14, so I think this is actually 14 for us. If you can imagine, This is a long relationship.
Yeah, we've been through this a long
This
time.
has been a great time. Yes,
All right.
absolutely.
So as Mr. Garrison said, I'm here today to talk to you about the origin of the elements. And I think one of the more amazing things that we know today is we know that the world is made of atoms. And it's kind of a silly thing, right? You learned it way back in elementary school, but that was an amazing piece of information that the world is made of atoms. In fact, it's such an amazing piece of information that the famous physicist Richard Feynman was once asked if all of human knowledge should be lost, and you could pass just one sentence to the next generation to rebuild human knowledge, what would that one sentence be? And that one sentence that Richard Feynman said is that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. He thought that that was the most important sentence that we could pass on if all of human information was lost. And so I'm here today to talk about the origins of the atoms that make up you and me, the atoms that make up this room, the atoms that are in our jewelry. For example, where did the gold in my wedding ring come from? So I want to talk about those atoms. I want to very briefly talk about the fact that astronomers know what distant things in space are made of, even though we've never been there. This cluster of stars is tens of thousands of light years away from us. We've never been there. In your lifetime, we will never get there. In fact, we've not even left our own solar system yet. We've not even traveled to the nearest star, let alone traveling to a star system like this that's thousands of light years away. So we've never been there. We never will get there, not in my lifetime, not in your lifetime, not in your great-great-great-great-grandchildren's lifetimes. But I can tell you exactly what these stars are made of. And they're made of the same stuff that the sun is made of. They're 74% hydrogen, about 25% helium, and about 1% everything else. How do astronomers know that, even though we've never been there? And the answer to that is we use something called spectroscopy. We take light and we break it into its component colors. You've probably seen at some point a science demonstration where you take white light and pass it through a prism, and that light gets dispersed into a rainbow of colors that looks something like this. If we do that for a white light in the classroom, we see all the colors of the rainbow. If we do it for the sun, we see that particular colors are missing. You notice there's one color of red light that's missing, a color of yellow light that's missing, a couple colors of green light, a blue-green light that's missing right there. Those missing colors come from elements in the star, in particular elements in our sun that are absorbing those colors. If we take those same elements and we excite them to glow, either by heating them up or running electricity through them, they emit those colors of light. And one of the ones, hydrogen, which makes up, you'll remember, most of the sun is 74% hydrogen. It gives off a red color of light, a blue-green color of light, and a couple blue colors of light. Those are exactly the colors that are missing here because the hydrogen atoms in the sun are absorbing that red light, that blue-green color, and those two blue colors right there. So our sun, mostly made of hydrogen, we know that because we can take a spectrum of our sun. And this is the kind of research that I do. I work with telescopes here on Earth. This is a telescope that the University of Virginia has access to in Arizona, called the Large Binocular Telescope. It's the largest telescope in the continental United States right now. I've done projects with the Hubble Space Telescope. Before coming to the University of Virginia, I worked on a NASA mission called the Far Ultraviolet Spectroscopic Explorer. And all of these telescopes have devices on board that break light into its component colors so that we can tell what distant things are made of. In fact, even today, I do work with the Green Bank Telescope, which is a giant radio telescope in West Virginia, where we can do the exact same thing for molecules, things like water molecules and ammonia and methane. All of those molecules emit radio waves, and so we can actually determine where they are in space and how much of them there are using giant radio telescopes like this. My goal today is to talk about the origin of everything on the periodic table of elements, and a couple elements that I'm really interested in that we're going to focus on today. One is element number 79, which is gold on the periodic table. And I'm interested in that one because it's valuable, right? And most of us, it turns out, are carrying a piece of gold around with us. So in my case, I've got a wedding ring that's got gold in it. Some of you have a necklace that has gold or earrings that have gold in them. You might have a watch that has some gold or a pair of eyeglasses that has some gold in it. If you're not carrying any gold jewelry, if you're carrying one of these, and I imagine most of you are carrying a phone with you, cell phones contain a tiny little bit of gold in them because gold is an excellent conductor of electricity. It's used in all modern electronics. So you've got a little bit of gold in your cell phone. But the other ones that I'm interested in, because they're really personally interesting to you and me, are carbon, nitrogen, oxygen, the things that make up a human being. And so the first question I have for you is, what are you mostly made of? What is a human being mostly made of? Water. Right? A human being is mostly made of water, right? We have to drink lots of water every day. Most of the mass of our body is in water. And what is water mostly made of? Hydrogen and oxygen, right? It's H2O. So at first thought, you might think, well, water is mostly hydrogen because there are 2 hydrogen atoms and just 1 oxygen atom. But astronomers and physicists think about it a little bit differently. We think about in terms of the mass that goes into making them. So those hydrogen atoms, if you look on the periodic table of elements that you've got there, the atomic mass is on the bottom right below the H, and you'll see that hydrogen has an atomic mass of about 1. Oxygen has an atomic mass of about 16. So the 2 hydrogen atoms combined have a mass of 2. The oxygen has a mass of 16. So it turns out that you are mostly made of oxygen. In fact, what a human being is made of is about 65% oxygen, only about 19% carbon or so, then about 10% hydrogen, a little bit of nitrogen, and then everything else just makes up a few percent of a human. But you are mostly made of oxygen. Another interesting question is, what's the most common element in this room? And now, but I look at this room and I think, well, there's the air in the room, but the air in the room doesn't have very much mass to it. Certainly not as much as the walls that we're looking at. And in this room that I'm looking at, probably same for most of the schools out there, I'm looking at mostly cinder block walls. What are those walls mostly made of? Carbon? Here, one choice. What else do you think? So how many people have made concrete in their life? What are the 2 of the main components of concrete?
Water.
Water and the mix. And what's the mix got a lot in it? Yeah, and no, he's exactly right. Water and concrete mix. But a big part of the concrete mix is sand, right? So what's water mostly made of? Oxygen. What's sand made of? Silicon dioxide. Right? It's quartz, it's crushed quartz. It's silicon dioxide. A silicon atom, if you look up there on the periodic table of elements, weighs about 28. How much do those 2 oxygen atoms weigh? 32. So silicon dioxide, quartz, is mostly made of oxygen. So between the sand and the water that goes into these cinder blocks and building concrete, concrete is mostly oxygen. It turns out that oxygen is one of the most abundant elements in the universe. Hydrogen is one of the most abundant elements in the universe. Carbon is one of the most abundant elements in the universe. You are made of the very common chemistry of the universe. So the first question I want to ask about the periodic table of elements is this everything that we know about? Are there other elements that could be out there? In particular, a question that often comes up is that if a UFO lands on the front lawn of the White House, is it going to be made of elements that we don't have on the periodic table? Something I want you to realize about the periodic table of elements is it's not just the elements we know of. It's actually all the elements that there can be. There can be no elements that something is made of that's not currently on our periodic table of elements. Let me explain why that is. So when Dmitry Mendeleev first invented our periodic table of elements, he did it sideways. Instead of doing it like it is today, he turned the whole table sideways. And you'll notice that in Mendeleev's periodic table of elements, every now and then, for example, for element 45 there was a question mark. He realized that the periodic table wasn't just a way for humans to organize the elements that we knew of. It was telling us something about the structure of atoms and how atoms are put together. And as he laid out the periodic table of elements, he kept finding these holes on the periodic table that indicated there should be an element there, but it hadn't been discovered yet. And then scientists went and looked and found eventually those elements. Now, the reason I can confidently state that this is all the elements that things can be made of is because of the way the periodic table is laid out. In the upper left corner of every element, there's a number, and you'll all remember from chemistry, of course, that's the atomic number for the element. And that tells you how many protons there are down in the nucleus of the element, right? The nucleus contains the protons and the neutrons, and the electrons are found in a cloud surrounding the nucleus. And the atomic number is the number of positively charged protons down in the nucleus. So hydrogen, for example, has 1 proton, so it's element 1. Helium has 2 protons, so it's element 2. Carbon has 6 protons, so it's element number 6 on the periodic table of elements. And the atomic mass is just the number of protons plus neutrons added together. So hydrogen is still just 1 because it has no neutrons. Helium has 2 neutrons and 2 protons, so its number is 2, but its mass is 4. And then carbon has 6 protons and 6 neutrons, so its atomic mass is 12 and its atomic number is 6. The thing about protons are, you can only have whole protons. You can have 1 or 2 or 3 or 4, or you can have 42 or 43 or 44, but you can't have 42 and a half or 43 and a half. You have to have either 42 or 43. And if you just count the numbers on the periodic table, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and on up the periodic table, you'll notice that there are no missing numbers anywhere on the periodic table. As I said, that wasn't true with Mendeleev. Mendeleev had missing numbers, but today we have no missing numbers. And even like element number 43 right here, element 43, technetium, 120 years ago, that element didn't exist, or actually about 100 years ago, that element didn't exist on our periodic table of elements. There was a gap there. And that's because there's no stable form of technetium. All forms of technetium are radioactive. Most common form of it decays within a couple days. And so technetium didn't exist on the periodic table until we had nuclear reactors where we could make it. You might say, well, aren't they always finding bigger and bigger elements down here at the bottom of the periodic table? For example, the biggest one that we have right now is 118, and scientists are working really hard to make 119 and 120. The thing you know about all these elements down here in this bottom row, in fact, everything from uranium on up, they're all radioactive. And these giant elements that we can make in the laboratory today, not only are they radioactive, but their half-life is usually measured in fractions of a second or seconds, or at best a few hours. These things last for such a short period of time that we can make them in the laboratory sort of one atom at a time, and then those individual atoms decay away very quickly. You couldn't make something out of element 118. This is an old periodic table, so it's still called ununoctium. So we've got the name up there. I can't even remember. Yeah, I can't even remember what 118 is called. And the reason I can't remember is because we can't make anything out of it, right? It lasts such a tiny fraction of a second that we can't build anything out of these. You can't make a UFO out of element 118 because it all decays away in less than a second. So our periodic table is everything there is in the universe that's made of matter, I should say. All right, so let's talk about where these elements came from. And the first thing we need to talk about is the components that make up the atom. Where did the protons, the neutrons, and the electrons come from? They came from the Big Bang. And so the next time, I know you're all young, but Mr. Garrison and I, sometimes we get out of bed in the morning and we're feeling kind of old and kind of creaky. It's really hard to remember when you look at your hand, the stuff that you're made of, the protons, the neutrons, and the electrons were made in the Big Bang. They are 13.8 billion years old. The stuff that you are made of goes right back to the origin of the universe. You are made of stuff that's 13.8 billion years old. And the question is, how do we know that? You need to
On Zoom, they are saying I'm in the wrong mode.
You're in the wrong mode. Okay.
Yeah, so let me, hold on just a second, guys.
Okay.
Hold on just a second. Still the same. Sorry, kids, sorry about this.
So at the top of that screen right there, where it says
Yeah.
display settings with the downward arrow.
That one right there, will that help it?
Yeah, that's what we want.
Okay, very good, thank you.
Okay, sorry about that. All right, so the stuff that you're made of was made in the Big Bang. How do we know that? Well, the answer is that the Big Bang has been not only studied in theory, that is, we can take the laws of physics as they exist today and run them backwards in time and figure out what the universe was like early on, but we can actually recreate the conditions of the Big Bang right here on Earth. And this is what we do in giant particle accelerators like they do in CERN, which is on the border of France and Switzerland. We can take protons and smash them together. And for a moment, as those two protons meet head on, the temperatures and the pressures and the densities are the same as they were a tiny fraction of a second after the Big Bang. So we can not only compute what the Big Bang was like, but we can experimentally verify on Earth what the Big Bang was like by recreating those conditions here. And what we know from that is that your protons and your neutrons had an origin as light early in the universe. The early universe was very, very hot, was filled with high energy photons of light called gamma rays. And if two of these gamma rays came together, they could make a piece of matter and a piece of antimatter. The piece of matter, say a proton has a positive charge, the antimatter is the same as the proton, it just has the opposite charge. It has a negative charge instead of the positive charge. Now, what happened in the universe most of the time is you make a piece of matter and antimatter, well, those opposite charges attract one another. So the positive and the negative would annihilate one another and they would end up giving you back the light that you started with. But for reasons that physicists don't understand right now and then in the early universe, the universe would create the piece of matter and not create the corresponding piece of antimatter. Or it would create the corresponding piece of antimatter and the antimatter would decay and disappear out of the universe, leaving just the matter behind. We don't know why the universe did that. It's a very active study right now. My generation's worked really hard on it, and I'm sure that somebody in your generation is actually going to figure out the answer to that. And then you'll get to go and get that big giant gold medal, the Nobel Prize in Physics, because that's a really huge unsolved problem right now. But this is where the matter that you're made of came from. Came out of Einstein's E equals mc squared. If we want to make some mass, m, we need some energy to do it. And the energy came from these photons of light. And as long as those photons of light had enough energy, it could make the matter and the antimatter. Like I said, every now and then the antimatter didn't get made or it disappeared, and the matter was what's left behind. So the early universe made all these protons, neutrons, and electrons. And for about 100 seconds, the universe was hot enough that these protons, neutrons, and electrons could collide with one another in nuclear reactions to start building the elements on the periodic table of elements. So a proton would combine with a neutron to make a heavy form of hydrogen called deuterium. That could combine with another heavy form, another neutron to form another heavy form of hydrogen, tritium. That could make a helium atom. The helium atoms could make lithium atoms. They could make a little bit of beryllium, but the beryllium was unstable and it would decay away. So for about 3 minutes or so, the universe is able to start making elements. But remember, the Big Bang, the universe was expanding very rapidly. And it was expanding so quickly and getting cold so quickly that after 3 minutes, these nuclear reactions shut off. At the end of the Big Bang, what the periodic table of elements looked like was this. There was just hydrogen, helium, and a little bit of lithium. There was no carbon, no nitrogen, no oxygen, no iron, no gold, none of the heavy elements. So where did they come from in the history of the universe? The answer is we have to follow this gas through the history of the universe. This gas is initially spread out very widely in space, and gravity starts to clump it together. This is the baby picture for the universe. This is what the universe looked like when it was just 380,000 years old. It's the furthest picture that humans can take of the universe, and it's the glow left over from the Big Bang. And these little clumps that you can see are places where gravity is already starting to pull this gas together to make galaxies and stars. So galaxies, which are made up of hundreds of billions of stars, they're the building block of the universe. And inside galaxies themselves, they are made mostly of individual stars. And it's stars that provide a hint as to where all these other heavy elements come from. So in particular, stars like our sun survive deep down in their core by fusing hydrogen atoms into helium atoms. Every second inside the core of the sun, of our sun, the sun fuses about 600 million tons of hydrogen into about 594 million tons of helium every second. Every single second, the sun is fusing hydrogen atoms to make helium, and the helium has a little bit less mass than the hydrogen going in. And that little bit less mass gets released in the form of energy. That's where the energy for our sun comes from. But every second, a few million tons of matter are being converted to energy inside our sun. What's amazing about our sun is it can do that. It can lose a few million tons of matter every second, and it will do that for 10 billion years. And at the end of its life, after losing a few million tons every second, it will be less than 1% lighter than it is today. The sun is just an amazing nuclear furnace of reactions. So what's going on in the sun today is it's converting hydrogen atoms into helium atoms. This is what the sun looked like when it was born. This is what the sun looks like today. And if we look deep down in the core of the sun, which is on the left side over here, you'll see that deep down, well, sorry, here's the sun today in the middle one. In the sun today, the core is about half helium and about half hydrogen. At the end of its life, the core will be mostly helium with hardly any hydrogen left at all. Now, when our sun starts to die, it can actually combine helium into beryllium. Beryllium can combine with helium to make carbon. At the very end of its life, when our sun is a red giant star, it's going to convert hydrogen to helium, helium to carbon, and some carbon to oxygen. So stars like our sun, at the ends of their lives, can build up these elements on the periodic table. Now, the carbon and the oxygen in your body did not come from our sun, because our sun's not going to do this until the end of its life. But stars like our sun can make those elements. Bigger stars, which are even hotter down at their centers, they can actually combine oxygen atoms together to make silicon. They can combine 2 carbon atoms together to make neon. They can combine those elements with other elements to start building up on the periodic table of elements. Massive stars, because they're so hot in their core, have a lot of other nuclear reactions that they can go through, and they can turn carbon into oxygen, into neon, into magnesium, into silicon, into sulfur, into argon, calcium, titanium, all the way up to iron on the periodic table of elements. So massive stars can make elements all the way up to iron. The problem with iron, or the good thing about iron, is it's the most stable element on the periodic table of elements. It is more tightly held together than any other atom on the periodic table. So when a massive star gets there, that's as far as it can go. It can't turn iron into anything else. Now, at the end of its life, these massive stars look like a giant onion. Down at the center is a big ball of iron, and surrounding that is a shell of silicon fusing into iron. And then around that's a shell of oxygen fusing into silicon, and on and on. There's all these shells inside the star, and that iron core can't undergo any nuclear reactions. And eventually it gets so massive and gravity gets so strong that it collapses. And when it collapses, it causes the star to blow up in a titanic supernova explosion. This is a picture taken back in 1986 of a nearby galaxy called the Large Magellanic Cloud. And there's a star in there that blew up. There's the star. So if you look very carefully, you can actually see it on this original diagram there. That star blew up in one of these titanic explosions. And when these massive stars blow up, they return all those heavy elements out into the universe. All the carbon and the oxygen and the neon and the iron that the star made gets blown out into space. But at the same time, as that star's core is collapsing, the temperatures and the densities and the pressures are so high that it makes all the other elements on the periodic table of elements. So this is what the periodic table looks like today. This is what it looked like at the end of the Big Bang, just hydrogen, helium, and lithium. Stars like our sun can make up to oxygen. Massive stars during their lifetime can make up to iron. And in the 2 seconds that it takes that core of that star to collapse and cause the star to explode in a titanic explosion, the star makes everything else on the periodic table of elements. The reason gold is valuable to us is because it's rare. And it is rare because the universe only had a few seconds to make all of those elements that are heavier than iron on the periodic table of elements. Now, one recent idea that's come about is that some of these big heavy elements like gold and mercury and others are actually made when 2 dead stars called neutron stars, when they actually spiral around one another and merge with one another. We actually saw one of these events happen a few years ago in a distant galaxy. And in the process of these 2 merging with one another, it created about the same mass in gold as our whole planet weighs. And so we've seen these neutron star mergers are another possible way to make gold. So the thought that I'll leave you with, and then I'll take some questions because I think we're running out of time, is that your atoms, the atoms that you're made of, the protons, neutrons, and electrons were made in the Big Bang. And then your atoms were spread out into space, and you've been in stars multiple times in the history of the universe. But most of the times you were in a star, you weren't down in the core where the nuclear reactions were going on. You were in these outer layers. And when that star blew itself up, your atoms were returned back out into space. But you were then incorporated in the next generation of stars, and they blew themselves up and your atoms were returned back to space. And they were in the next generation of stars. And those atoms, those stars blew themselves up and returned those atoms into space. But eventually, the last time your atoms were in a star forming region, they weren't in the star at all. They were actually in this disk of material that surrounds the star. And it's this disk of material where the atoms eventually clump together to make rocks and asteroids and comets, and eventually clump together to make planets like the Earth. And so that's where your atoms got created along the way of the history of the universe and how you ended up in the Earth. The last thought I'll leave you with is, so what's the future for your atoms? Well, when our sun becomes a red giant star, it will actually get so big that it will vaporize the outer layers of the Earth. So after you die, your atoms will be returned to the Earth. They'll be recycled through other plants and other animals. And yes, I know it's kind of creepy to think about, but your atoms will be recycled through other people in the future. But at the end, when our sun vaporizes the outer layers of the Earth, it will form a beautiful planetary nebula like this. And your atoms will be part of this nebula. And that green glow that you see there in the center of the nebula, that comes from oxygen atoms. That is your future. Your atoms someday will be spread back out into space, where they'll be incorporated in the next generation of stars. So you came from the stars and you're going back to the stars about 5 billion years from now. So that's my quick summary of the origin of the elements. I'm happy to take questions on that or other questions in the time that we have left. Yes. Well, I think there's life out there. I think life in the galaxy is probably really common, but I think it's simple life, like possibly plants and single-celled algae and things like that. I don't think there's other intelligent life out there in the galaxy right now. I think we're alone. But here's the important thing. I don't think we're the first intelligent species in the galaxy. I think there have been many intelligent species before us, but they've all died off.
Do we have time to discuss the Fermi paradox?
Yeah, well, real quick. So for those that don't know, the Fermi paradox is a really interesting idea, which is that everything tells us that life should be common. There are hundreds of billions of stars in the galaxy. So you might think that life should be really common in the galaxy, yet we have no evidence that it exists. We've never seen life anywhere else. We have no idea that there's intelligent life anywhere. So that seems to make a paradox. There's so many stars, it seems like life should exist, and yet there's no evidence for it. There are many proposed solutions to the Fermi paradox. The one that I think is most likely, but is also the most depressing, is that intelligent civilizations, when they get to the level that we are at, not only do you finally have the ability to build radio telescopes to communicate with other civilizations, but you've also built nuclear weapons, you've got global warming, you've got the exhaustion of inexpensive fossil fuels, you've got overpopulation, you've got all these problems. And my fear is that intelligent civilizations end up destroying themselves before they can travel amongst the stars, before they can make themselves known. Yeah, that's.
Would you mind to share your email on the screen, and we'll share the screen then here after you get that written down. I know other sites you can't see this, but I will share this here in just a second. The email for Dr. Murphy. Very easy to remember, emm8x@virginia.edu. And so let me share that with everyone here. Okay, so let me share that screen with everyone.
You're sharing that, I'll take some questions.
Sure.
So we recently made like a huge technological leap in like smartphones and computer technology, and we were able to see how humans like were able to still adapt to that even with like really heavy impacts. Do you think that even if we were able to make the technological jump to space travel, do you think humans will be able to like actually adapt to that?
So I'll tell you that, but I think about space travel coming from somebody who's a big fan of Star Trek. Although I haven't seen Picard because I'm a chief paper Paramount. What do I think of space travel? Here's the thing to note, with the spacecraft we have today, to get to the nearest star, not our sun, but the nearest star other than our sun, Alpha Centauri, would take about 70,000 years with the best, fastest spacecraft we have today. 70,000 years, right? So we've never been there. And we're not going to get there in my lifetime, and we're not going to get there in your lifetime, and we're not going to get there in your great-grandchildren's lifetime. And you might say to yourself, yeah, I know, but we're going to do better than your generation, and you are. You're going to take what my generation did, and your generation is going to build on that. You're going to build even better spacecraft or even faster. And imagine that yours goes 10 times faster, right? If yours goes 10 times faster, now instead of 70,000 years, it's only going to take you 7,000 years to get to the nearest star. And you're still not going to live to see that travel. And imagine that your grandchildren do a factor of 10 better than you, so that their spacecraft are going 100 times faster than what we can do today. Their spacecraft is still going to take 700 years to get to the nearest star. And imagine that their grandchildren build something that can go 10 times faster than that, then it's still going to take 70 years to get to the nearest star. That's more than 1,000 times faster than we can travel today. And the thing is, we have maxed out what chemical rockets can do today. You can't improve on chemical rockets anymore. They're going as fast as they possibly can. So to even go 10 times faster than we're going today, you're going to need a whole new technology that we've never thought of. I can't imagine developing a technology that can go 1,000 times faster than we can go today. If that technology even exists, that is a long, long way in our future. So I'm sure that humans can adapt to travel through space. I'm worried about the technology side. I'm worried about the physics side of it, which is space travel is a lot harder than Star Wars and Star Trek. And then it makes it look. So, space.
We have a question at Stafford.
Yeah, go ahead.
What's your professional opinion on the whole teapot biosphere hypothesis? Is that a thing that's taken seriously either for Earth or other planets?
Sorry, I couldn't, you broke up there. Which hypothesis?
Deep pot, what was it?
The teapot biosphere hypothesis, is that a thing that's taken seriously for Earth or other planets possibly?
Deep pot biosphere.
Hypothesis?
Can you describe it quickly? I don't know it by that name. Can you describe it quickly?
The whole thing that instead of photosynthesis as, you know, the first process and origin of life, that it was the development of microorganisms under the crust feeding off of natural petroleum reserves.
So I'm not familiar with that one. The one that I'm most familiar with, the one that I would argue that the vast majority of scientists believe, is that the first life on Earth was chemosynthetic, but it developed around volcanic vents down at the bottom of the ocean. And that's because we see today very primitive organisms, their ancestors that still exist on Earth today. We call them extremophiles, and they are microbes, bacteria that live in really extreme environments. And based on genetics and looking at the genetic tree, they are as far distant from all the other things that exist today as anything else. And so they look very, very ancient to us. Those are the cyanobacteria and those bacteria that exist down around the volcanic vents at the bottom of the ocean.
I was hoping you could share with us, I know that in the past you have been studying the interstellar gases. What are you currently working on? I mean, you briefly mentioned you're working with these satellite or radars.
Yeah.
But what is it that you're actually looking for out there?
Yeah, so what I'm interested in is how these elements, as they're made in the stars, how they circulate around our Milky Way galaxy. And so I'm interested in how it gets from the stars to the next star forming region. In particular, I study a class of clouds called high velocity clouds, which are clouds that are actually falling into our Milky Way galaxy. And a long time ago, these were discovered by Dutch astronomers, big clouds of gas that are just slowly falling into the Milky Way. And the question is, where did these clouds of gas come from? One idea is that they're left over from the Big Bang and they're just falling into the Milky Way for the first time. And another idea is that when supernovae go off in the galaxy, these explosions of stars, they blow material up there that cools off and falls back down. And it turns out that neither of those explanations work really well. So the explanation we're working on these days is that our Milky Way galaxy actually builds up by cannibalism. It actually eats smaller galaxies. As smaller galaxies wander by the Milky Way, its gravity pulls them in, tears them apart, and their material becomes part of our galaxy. So we think that these clouds are actually the remnants of some of these galaxies that were eaten by the Milky Way. Yes.
What if it happens to our galaxy?
So our galaxy is on a collision course with Andromeda. So there are two big galaxies in our part of the universe, us and the Andromeda galaxy. And gravity is actually pulling the two of us together in about 3 to 5 billion years from now. Our two galaxies are going to merge together. Now, because we're equal size, it's hard to say that one is eating the other. We're going to merge together into a giant galaxy. What's really fascinating when galaxies merge like that is because stars are so tiny and they're so far apart that the first time these two galaxies pull together because of gravity, they'll actually pass right through one another and go out the other side. But the gravity will continue and then they'll end up mixing together. And we'll end up with one big galaxy in the very end, which is the combined stars and matter that were in both the galaxies to begin with. As they collide with one another, though, both galaxies will undergo a tremendous burst of star formation. For at least a short period of time, we'll be one of the most active galaxies in the universe.
What was the most recently discovered element in hydrogen?
What's the most recently discovered element? So all of the ones on the bottom of the periodic table, 118 is still the largest that I'm familiar with, but and I'm quite sure that we haven't discovered anything bigger than 118 yet because it's gotten really hard to make those big elements. So that's the last one that I'm aware of. And it's not in anything because we can literally make it one atom at a time in a big particle accelerator where we smash smaller atoms together to make the bigger atom. So. Yes.
You mentioned briefly dark matter and the creation of the universe. I saw a statistic that was like a large percentage of the universe is primarily dark matter or antimatter, dark energy.
Yeah.
And that it's extremely volatile when reacting with our just normal matter. Has there been any advances in the use of that as a potential energy source by harnessing the volatility?
Yeah, so the question for those that couldn't hear it is about dark matter. And I think there's a couple things that are mixed in there. So first of all, we see lots of gravity in the universe. Our own Milky Way galaxy, for example, is spinning so quickly that if we add up all the normal matter in our galaxy and add up the gravity from that normal matter, it can't hold our galaxy together. To hold our galaxy together, there has to be many times as much dark matter as there is regular matter. But the thing about dark matter is it's the opposite. It doesn't react with anything at all. In fact, there could be dark matter in this room right now, and it would just pass right through the room. It would pass right through you and me. It doesn't interact with normal matter, which is why we can't find it. Right? If it interacted with normal matter, then we could sense it, we could detect it. The only way we've been able to detect it is with its gravity. So that's dark matter. And then we also see that the universe is not just expanding, but about 20 years ago, a little more, about 25 years ago, it was discovered that the universe is not just expanding, but the expansion is accelerating and going faster and faster. And that comes from something called dark energy. We don't know what dark energy is either. By the way, the words dark refer to our knowledge of them. We just don't know what they are yet. Dark energy also doesn't interact with matter, and it's probably a property of space itself. That as space expands, that expansion is going to go faster and faster over time. But we can't harness either of those to make energy because neither of them interact with matter. I think the thing you're talking about that interacts with matter is antimatter. And if we could find a huge source of antimatter, it would make a fantastic energy source. The problem is the universe just made matter. It didn't make antimatter. So we can make antimatter in particle accelerators today. We literally make it one particle at a time, and it takes more energy to make them than it gets when we annihilate them because our processes are inefficient. So we don't, if we had a good source of antimatter, we could use that as a power supply, but that doesn't exist. And the thing is, it's not just that it doesn't exist here on Earth, it doesn't exist anywhere in the universe. Yes.
The general relativity theory says that wormholes are theoretically possible. Do you think that they are possible or that they actually exist?
We don't know. So general relativity says it's a possibility that wormholes exist. This usually leads into this question of could we use them to travel quickly to the nearby stars? And the answer to that is almost certainly absolutely not, because in order to make a wormhole, you have to make a black hole. And to make a black hole, you have to harness the same mass that we have in our sun and cram it into a ball that's just a few kilometers across to make a black hole. And that kind of, as hard as it is to imagine building a spacecraft that can go 1,000 times faster than today, imagining human beings harnessing a star and squeezing all that matter into a tiny space is just unfathomable to me. So they may exist, we don't know. But whether they'll ever be used for space travel, I highly doubt it. Any questions from online? Other questions from in here? Yes.
Do you believe in ghosts?
Do I believe in ghosts? I do not. And I do not believe in ghosts for the same reason that I don't believe in Bigfoot and I don't believe in UFOs. And the answer is, imagine that an alien walked through that door right now and came up here and shook hands with me. What would I hope that at least some of you would do in this classroom? Would what?
Take a picture.
Take a picture of it, right? How many of you, just out of curiosity, are carrying a camera with you right now? Right? Look, how many cameras there are in this room. So I would hope at least Mr. Garrison would get his camera out and get a really good TikTok video of me shaking hands with this alien, right? Here's the thing. Every single human on Earth today is carrying a really sophisticated camera with that. And what's the best evidence we have for UFOs? Really lousy pictures of blurry things in the sky. Or what's the best evidence we have for ghosts? Really blurry pictures of things. What's the best evidence we have for Bigfoot? There's not a single good picture of Bigfoot out there, right? If these things existed, because everybody's carrying a camera with them today, you'd have lots and lots of pictures of them. So there's lots of reasons to not believe in these things. And again, I don't believe in them because there's no evidence for them. And as a scientist, I'm evidence-based. Without the evidence, I'm surprised that we don't have better evidence if they really exist.
One more thing, can you on the board, when do you have outreach normally down at your observatory in the UVA camp?
That's right. So we're open on the first and third Fridays of every month. So if you want to come down and look through the telescopes at UVA, you can come down on the first and third Fridays of every month.
It's Friday. It's Friday.
Yes. Yeah, we'll be open this Friday. Yes.
What would you say is like the most interesting thing you discovered or learned?
The most interesting thing that I've discovered. When I was a graduate student, I was doing a project at a big radio telescope in Green Bank, West Virginia, and we were mapping a part of our Milky Way galaxy. And I saw this big giant bubble that no one had ever seen before. And it was one of these bubbles that's blown out by supernova remnants. We call them super bubbles. And it was just kind of cool because I had the same experience that Clyde Tombaugh had when he discovered Pluto, as I realized that I was the first human being in history to know that this bubble is out there. And then for a little while, I was the only human being to know that this thing existed. And that's the real excitement of science, is making discoveries like that, where you realize you're the first, and for a few minutes, at least the only person. Of course, I couldn't contain my excitement. I ran down the hall, told my advisor about it. He ran in, he looked at it, he took the data, he double checked to make sure that I hadn't made a mistake. And so that was kind of cool. That's the, so that's my sort of big discovery moment. I did that. But that happens in science a lot, where you get to discover something and you're the first person to see something. Other questions?
Right. There's no other questions from the other sites. We'll discontinue the broadcast. We'll let you get back to your other classes. Again, thank you for the great questions. Thank you for the time together. Dr. Murphy is available. If you want to email him, go take your campus tours at UVA and give him connections so that he can talk with you while you're on campus there. Just make these personal connections. Take advantage of the opportunities that are in only CGS. So thank you guys so much. I hope that you have a great afternoon and